So something which is as fine as a hair, for example, that could qualify as being a microfluidic device. So in this context, there are several biomedical devices, sensors, which work on the principles of, or rather, which work on various effects that you see at microfluidic domains only. Things which you do not see at microscale flows. What do I mean by microscale flows? Say a flow through a pipe. When you open a tap, water starts falling out. That is not microfluidics. It is normal fluid mechanics. It falls under the study of flow networks and all these things. So, in general, flows at small domains. Let's try to put some examples on the board. So, flow inside the human body. This also includes the transfer of oxygen from air to the capillaries. At the ultimate stage, it goes down to the micron level where the transfer happens. Then, so this is oxygenation. Then you have transfer of ions. So at the cell membrane, at the cellular level, there is a transfer of ions such as calcium and potassium. Even that is regulated by various signals that happen at the small scale. Inside the cell, the protoplasm that is there, that also plays a major role. How the functioning of a cell is regulated by such things, it has a very close dependency on the mass transfer and heat transfer happening at extremely tiny scales. Less than 10 microns, less than a micron. Okay. Apart from this, flows that happen in soil, or what Professor Mitra spoke about, adsorption, the process of adsorption, ultimately, so flows in porous media. Despite the actual media being very large, say you want to analyze the flow through a reservoir, underground reservoir, right? That flow is happening at a very large scale. Maybe it is as large as hundreds of kilometers. But if you keep shrinking down the scale, you will see that the pore sizes that comprise of the rock or the compacted sand or alluvial soil, the pore sizes are typically 50 micron to 100 micron. And the entire physics that happens at the microscale is then essentially upscaled to what you see at the microscale. So we say that the pore scale is Stokes flow. At the pore scale is Stokes flow. Whereas if you upscale this flow now, you upscale the flow, meaning you don't have to analyze a very small control volume over there. You analyze something in meters. The Gauni equation then upscales to the Darcy equation. These are very common. So Darcy equation, the genesis of the Darcy equation was purely based on experimental evidences. It was done by a hydrologist in France way back. And he saw that the total amount of discharge that he had was a function of the pressure gradient. But several decades later, it was shown that the Darcy equation is a fundamental consequence of integrating what you see at the pore scale through a rigorous method which is known as method of asymptotic expansion. So, at the end scale, at the smallest scale, adsorption. What is adsorption? He defined adsorption as a surface process where something gets attracted at the surface, not at the bulk. So at the very end of that attraction stage, the forces that overcome will be typically the van der Waals forces. You've heard of this thing, right? Van der Waals forces or the short range interactions. But far from the object, there will be hardly any potential to drive the molecule towards the surface. So even this physics, the isotherms, the Langmuir isotherms and all these things, they have their genesis in the study of microfluidics. So microfluidics was not always known as microfluidics because many colloidal scientists, many engineers, many physicists used to study all this in different contexts. They used to analyze all these things in different contexts, and it was only a few decades earlier that this term was coined, and it was borrowed from the word electronics. Because you will see that the methods to make electronics are very much aligned with the methods to make microfluidic devices. Hence, electronics, microfluidics. It encompasses all the things micro, fluid, and X from electronics. Right? Alright. Why is there such a fundamental difference between flows through pipes that you see and or a flow of a waterfall or a river and the flow in such miniaturized scales? The main difference is the scales involved. So suppose you have a pipe. Suppose you take a pipe and it has a diameter of d, right? And suppose the length is capital L. So the volume of this entire thing is pi d square L by 4. Right? So now, if I look at the surface area of this cylinder, what will be the surface area? Surface area is pi d into L. If I divide these two, so I have pi d L by pi cancels out, d cancels out, L cancels out, so I get 4 by d. So this ratio, let us look at what happens to this ratio. As d keeps on reducing, if the diameter keeps on reducing, what happens to the ratio of the surface area to the volume? So this is basically surface area by volume. If d keeps on reducing, what will happen? This ratio will keep on increasing. So it means that at the small scale, the physical effects which are now dependent on surface area will start dominating over the physical effects which depend on the bulk. Right? What are some examples of physical effects which depend on the bulk? The weight of an object. If you have more bulk, it has a larger weight. Right? Things like that start to become less and less important at the micro scale. That is why in analysis, you will never hear that the weight of the red blood cell is important in analysis. No, because the sizes are shrunk so much that only the surface effects are more important. What are some examples of surface effects? Some things which depend on surface area. Surface tension, for example. That depends only on the surface area, not on the bulk. So as you can imagine, when you shrink dimensions to a very small scale, surface tension effects become very important. That is true. If you have ever done some painting with those brushes, right, you will see that the brush tends to stick together the finer the hair is. For brushes used for wall painting, they are very thick in nature. They don't stick together all that well, right? So those fine, as the brush becomes finer, you will be able to draw finer strokes, better calligraphy, right? Alright. So surface tension is one such effect. Electromagnetic fields. When the domain shrinks, right, the flow of fluids can be affected by electromagnetic fields. And this lecture is all about this. Can be affected by electromagnetic fields, but it is a very common occurrence. It is more common than you think. Here's something you can try at home. You take a balloon, right? You inflate the balloon. Take the balloon, inflate the balloon. You take a towel, or if you have a silk cloth, it's even better. You rub it several times. Then you open a tap and just take the tap should not be it should not be opened completely. It should just be opened so that some stream of water is falling. You take the balloon, the water will deflect. This is something which you might have done as a child. So what are we doing over here? First of all, we are doing triboelectric charging. This kind of charging is called as triboelectric charging. So the voltage difference between the water and the balloon reaches some tens of kilovolts. Charge is less, the amperage will be less, but the voltage difference is tens of kilovolts, and it is able to bend the stream of water. It means that the interface between air and water is affected by the presence of a strong electric field. Similarly, if you take an even thinner jet of water, it will be bent even more, right? So it means that as the dimension becomes thinner in that case as well, the force acting on it will be larger. In fact, we all know from basic electrostatics that the electric fields are larger wherever the feature sizes are small. Whenever you have kinks in the object, the field strength increases because the gradient is across a very small distance. So I'll just try to elaborate on this a bit more. So the electric field is essentially negative of the gradient of potential, right? The electric field is the negative of the gradient of the potential. So the gradient, what does the gradient mean in this case? So if you have two lines, the gradient between these 2 points will be phi1 minus phi2 by delta x. Right? So the delta x shrinks. If the delta x is small, what will happen again? You get the same effect. The field strength increases manifold and you get certain disturbances at the interface. So that is the sense why this water jet bends is this. In fact, if you have certain kinds of lip gloss, women use lip gloss. Certain kinds of lip gloss in winter, they show a very remarkable effect. Suddenly you will find this lip gloss streaming away for no apparent reason. But the streaming away of lip gloss in winter is happening because of all the static charge that happens in winter. In winter, things have larger static charge than in summer or rainy season. So the streaming of the lip gloss is solely because of that static charge creating some voltage difference and the fluid jumping towards it. In fact, it tries to follow the isoelectric field lines. Alright, temperature gradients. Again, the gradient of temperature will depend on delta x, 1 by delta x. Smaller the feature size is, larger is the expected effect. But that is of course a bulk effect. But in general it gets combined with several other surface effects. For example, surface tension. Surface tension is a function of temperature. Is it? Yes, it is. How do we know it? No. Some childhood experiment can you describe which convinces someone that surface tension is indeed a surface effect which depends on temperature? Any childhood experiment that's a
bubbles, what air bubbles is
no, air bubble is there, but how it depends on temperature. So I'll describe a simple experiment. You take a boat like this. Take a piece of cardboard and you put it on water. What do? You place a small, one of those flat candles with the metal base. Very popular in Diwali, right? Flat metal base candle. When you light it, what will you see? It will start propelling. Why is it propelled? By the way? It's because the surface tension over here is lower than the surface tension over here. Okay? So this higher surface tension is trying to pull this boat towards itself. Similar thing happens when you put camphor. Instead of this hot thing, you put camphor. What is camphor? So when you put that, you will see again it start. But it will stop accelerating after a certain time. It will stop. When will it stop? Huh? It will stop when all the camphor has dissolved in the water. So there is no more gradient of. So if I call the concentration of camphor C, right? Over here it is C, over here it is 0. So there is a gradient of C, right? Gradient of C exists. It's not so good. But if gradient of C exists, so the gradient of sigma will also exist. So gradient of sigma means surface tension gradient. That is why it gets the force. Similarly, the same is valid for T as well. The same is valid for T as well. Gradient of T is gradient of surface tension and there is propulsion. You can try this at home. You can try many of the things what you are doing, you can try them at home. Just because it is microfluidics doesn't mean you need a bunch of high-end research facilities. You need to be creative. You need to be creative. Actually, children do a lot of fantastic things. Children in arts and craft, they do fantastic things, but it is passed off as arts and craft. That is the thing. Alright. So now the next question is, how far can we go in the microscopic domain? Like I said 100 microns, right? Can I go lower? Of course, I can go to 10 microns. Red blood cells are like 3 microns to 10 microns. Red blood cells. I can go lower. I can go to 100 nanometer. I can go to 50 nanometer. I can go to 3 nanometer. I can go to no one is stopping me. I can keep saying these numbers. I can keep reducing the numbers. I can keep reducing the numbers further. But when do we stop? We stop when we are no longer in what is known as the continuum framework. Continuum hypothesis is a hypothesis which says that the field description of this kind of flows is valid. What do we mean by field description? Actually, all things are comprised of atoms, molecules, right? So, in reality, we should be describing the equations of motion for all the atoms and molecules. For example, this bottle of water. This bottle of water is 500 ml, right? 500 ml of water. How many moles of water does it contain? How many moles? All these things rings a bell. Moles. 1 mole of water. Equal to how much? 80. Huh? 18 gram per liter. 18 gram. So it is 18 gram per liter. So this is how many liter? Half liter. So no, it isn't. So we have to do the back calculation. Essentially, let's say for very simplicity's sake, say this contains 1 mole of water. It does not, it contains 55.55 or something like that. But it is 6.023 10 to the power 23 molecules per liter. Right? So now you have this molecule, this molecule, this molecule, this molecule, this molecule. You have so many molecules, right? And now you have to say, alright, I'll do it the hard way. For this molecule, I'll find out if I call this molecule because of all the other J molecules where J is not equal to 1. Right? I'll find out the force on the Jth molecule by all the force on the ith molecule by all the other J molecules where J is obviously not equal to 1. It's not itself. What are these interactions like? They could be electrostatic. They could be like for planets. You can do the same calculation for planets also. How? For suppose this is Earth. So the planet I is Earth. So what will you do if you want to do the calculation for Earth? You will find out the force acting on Earth due to the moon plus force acting on Earth due to the sun plus force acting on Earth due to the planet Mercury plus Venus plus Uranus plus Saturn and so on. So for a very small system also, for one planet you have to loop over all the other planets. For the other planets, so similarly, for the force acting on Saturn It will be Saturn due to Sun plus Saturn due to Mars plus Saturn due to Earth and so on. So each time you have to do so many calculations. At the end of the calculations, what do you do? So you have the force is equal to mass of the planet, or here in this case mass of the atom or molecule, whatever it is, times dV/dt. The force acting on that molecule will be this. Then what do you do with this information? What do you do with this information? So suppose now you know you have calculated all the forces and all, and you now know what do we do with this? I mean, just with this, we can integrate it in time. We can integrate this equation in time because it's a ordinary differential equation, right? Integrate this in time to get the new location or the new velocity. With the new velocity, you get the new location. So if this is the snapshot at t equal to 0, the snapshot at t equal to some delta t will look like this. The particles have been displaced because of all the variety of forces acting on the various particles, or it could be molecules or atoms or whatever it is. Right? What do we do with this? How does this molecular level description aid me in anything at all? How? Oh, there is some framework. This is called as statistical mechanics. There is an entire framework set of rules. In statistical mechanics, you can do various averages. You can find out various statistics and thereby conclude various properties that you see in bulk. We've already discussed what this method means. This method is simply upscaling again. You are upscaling the information at molecular level. You are taking the information happening at the molecular level up to something which you can see, something which you can feel, like temperature, for example. You might have heard of this, but temperature is a manifestation of the kinetic energy of molecules, right? So if I have all the molecules and all the velocities, I can simply find out summation Ke I for I equal to 1 to n, right? And this will be equal to half kT by something called as the equipartition theorem, where K is what? The Boltzmann constant. So this entire framework was laid down by